In this lesson, we will determine the extrema of functions of two variables. So after this lesson, you must be able to locate the relative maximum, the relative minimum, or the saddle point of a given function using the second partial test for optimality. Extrema of functions of two variables. Imagine the graph of the function z equal to f of xy, that of a mountain range, and that the mountain tops are the high points in their immediate vicinity, and these are referred to as relative maximum of the point f, and that the valley bottoms are the low points in their immediate vicinity, and these are referred to as relative minimum or minima of the function f. That the largest and smallest values of the function f of xy over the entire domain of f are called the absolute or global maximum or absolute or global minimum values of f respectively. Now, a point p x of 0, y sub 0 in the domain of the function f of xy is called a critical point of the function if the partial derivative of f with respect to x evaluated at x0, y0 is equal to 0, and the partial derivative of f with respect to y evaluated at x0, y0 is also equal to 0. Or we have the case of one or both of these partial derivatives does not exist at x0, y0. Then the critical point p x0, y0 may be a maximum point, a minimum point, or a saddle point. To determine whether the critical point is a maximum point, a minimum point, or a saddle point, we will be using the second partial test for optimality as given here. Okay, so if we recall, we did this already in the previous lesson. Okay, let us work out some examples. We have to locate all relative maxima, relative minima, and saddle points, if any, given the function f of xy equal to x squared plus xy plus y squared minus 6x. For our solution, the first thing that we'll have to do is to locate the critical points, and these points are points where the first partial derivative of f with respect to x and the first partial derivative of f with respect to y are both equal to 0. So if we're going to satisfy this condition given the function f of xy, then the partial derivative of f with respect to x will just be given by 2x plus y minus 6, that we equate to 0. And that the partial derivative of f with respect to y, which is given by x plus 2y, is also equated to 0. If we do it this way, then we come up with two equations in x and y. What we need to do is to determine the values of x and y for which the partial derivative of f with respect to x would equal the partial derivative of f with respect to y, both equal to 0. So working as a system of equations, we now solve for x and y. And we do it here by substitution, where from this equation we have x equal to negative 2y. And if x in this equation of the partial derivative of f with respect to x is replaced with negative 2y, then this first equation would be transformed to 2 times negative 2y plus y minus 6 equal to 0, which is just an equation in the variable y. And as such, you will be able to solve for y, and y is equal to negative 2. Now, using y equal to negative 2 and substituting that in this equation, we will be able to solve for x, and x would take on the value of positive 4. So at this point, we have the point x0, y0 given by 4, negative 2. This is our critical point. This is a point satisfying the partial derivative of f with respect to y equal to the partial derivative of f with respect to x equal both to 0. So now the next step is to determine on whether this point is a maximum point, a minimum point, or a saddle point. So we test for optimality using the second partials test. Okay? And here we need to do the second partial derivative of f twice with respect to x, the second partial derivative of f twice with respect to y, and the second mixed partial derivative of f, all evaluated at the critical point for -2. And that the second partial derivative of f twice with respect to x would just be given by 2. That is obtained differentiating this again with respect to x, holding y constant. And if we take the derivative of the partial derivative of f with respect to y again, then this second partial derivative of f twice with respect to y would just be equal to 2. And differentiating this with respect to y or that with respect to x would give us the second mixed partial derivatives, both equal to 1. Okay? So, with these values, we are able to determine the value of d by substituting accordingly these values in that expression there, coming up with d equal to 3. Now, d is with positive value. So either we have a maximum point or a minimum point. Now we check on what the value of the second partial derivative of f twice with respect to x. And since the value there is also positive, we conclude that at the critical point, we observe a relative minimum. To summarize what we had in this lesson, the extrema of a function f of xy are observed at points where the partial derivative of f with respect to x is equal to the partial derivative of f with respect to y equal both to 0, and that the relative maximum or the relative minimum or the saddle point of a function can be determined using the second partial derivative test.